Have you ever stood on an escalator and wondered how thousands of metal steps move in perfect synchronization without ever jamming or collapsing? The handrail glides at exactly the same speed as your feet. The steps flatten seamlessly at the top and bottom. Hundreds of people can stand on it at once, and it keeps moving. What kind of engineering makes that possible? Where does all that power come from? And how does a machine designed to run continuously for decades never seem to break down? In this video, we'll break down that mechanical puzzle step by step. At first glance, an escalator seems like a simple moving staircase. It carries people between floors without them having to walk. But in reality, it performs one of the most demanding tasks in any building. It moves thousands of people per hour through confined spaces while maintaining absolute precision and safety. A single failure can shut down entire transit stations or shopping centers for hours. In its basic form, an escalator is a loop of steps pulled by a continuous chain drive system. But unlike an elevator that simply moves a platform up and down, an escalator must transform flat landing areas into angled stairs and back again, all while supporting live loads that shift with every passenger. That transformation happens seamlessly because every component is synchronized to a tolerance of less than 1 millimeter. For a long time, people assumed escalators were just powered conveyor belts at an angle. The motor turns, the steps move, and that's it. And yes, the motor does matter. But motor power alone doesn't explain why the steps stay perfectly aligned. It doesn't explain why the handrail moves at exactly the same speed. And it certainly doesn't explain how the steps disappear and reappear without crushing anything in between. The real engineering challenge isn't moving the steps. It's controlling them with absolute precision under constantly changing loads. That's why escalators rely on a chain and sprocket system hidden beneath the steps. At the top and bottom of every escalator are two massive drive sprockets, each connected to a looped roller chain that can span over 30 meters in length. Every step is mounted on 4 wheels, 2 on each side, and these wheels ride along fixed steel tracks, precision machined to tolerances of less than half a millimeter. As the drive sprocket rotates, it pulls the chain, which in turn moves the steps along the tracks in a continuous loop. This system ensures that every step moves at the exact same speed because they're all mechanically linked to the same drive chain. The chain itself is constructed from hardened steel links, capable of withstanding tens of thousands of kilograms of tension force, without stretching or breaking under normal operating conditions. The source of this motion is a powerful electric motor located in the machine room, typically found at the top or bottom landing platform. The motor drives a gearbox that reduces rotational speed while increasing torque. This gearbox is critical because escalators don't need high speed. They need consistent pulling force capable of moving several tons of human weight at a steady, controlled pace. The output shaft of the gearbox connects directly to the main drive sprocket, transferring rotational energy directly into linear motion of the step chain. To ensure smooth operation, modern escalators use a variable frequency drive that controls motor speed electronically with precision. This system allows the escalator to ramp up gradually rather than jerking into motion. It enables energy-saving modes during low traffic periods, where the escalator slows down or stops entirely until a passenger is detected by infrared sensors at the entrance. When someone steps on, the system accelerates smoothly back to full speed within 2 to 3 seconds. One of the most unusual features of an escalator is how the steps change shape during their journey. At the landing zones, the steps must flatten out to create a safe boarding area. But in the incline section, they must form a traditional staircase with precise riser heights. This transformation is controlled by the track system. Each step has 2 sets of wheels. The rear wheels follow the main track that determines the escalator's incline angle. But the front wheels follow a separate return track that flattens out at the top and bottom. As the step approaches the landing, the front wheels rise along the return track, forcing the step's tread to level out horizontally. The reverse happens at the opposite end, creating the staircase formation again. This continuous transformation occurs smoothly because the track curves are precisely calculated to prevent sudden changes that would jar passengers or stress the mechanical components. Unlike elevators that can shake or wobble under load, an escalator must remain rock solid even when packed with passengers during rush hour conditions. This stability comes from the truss, a massive steel framework that supports the entire assembly. The truss is engineered to handle loads far exceeding normal capacity, typically rated for 2 to 3 times the maximum expected passenger weight. It's anchored into the building structure at both ends and remains completely rigid, regardless of how many people are standing on the steps at any given time. Operating an escalator safely requires multiple redundant systems working simultaneously. The first line of defense is the brake system. If power is lost or an emergency stop button is pressed, spring-loaded brakes clamp onto the drive shaft instantly, stopping the escalator within a controlled distance. These brakes are fail-safe, meaning they engage automatically without requiring electrical power. Even if every system fails, the brakes will stop the machine. But escalators face a unique challenge that elevators don't. If the drive chain breaks or the motor fails catastrophically, gravity could cause the steps to roll backward, creating a dangerous reverse motion. To prevent this, escalators use a secondary mechanical device called a no-back brake or anti-reverse ratchet. This component allows rotation in only one direction. If the steps try to move backward, steel pawls engage with a ratchet wheel, locking the system in place immediately. The escalator simply stops. It cannot run in reverse under any failure condition. Continuous exposure to vibration and mechanical stress over years of operation creates serious maintenance challenges. Every moving part in an escalator experiences wear. The step chains stretch over time. The wheels develop flat spots. The tracks accumulate debris. Without proper lubrication and regular inspection, these issues compound until the machine becomes unsafe or inefficient. That's why modern escalators include automatic lubrication systems that deliver oil to critical wear points on a timed schedule, reducing friction and extending component life. Another critical but often overlooked system is the handrail drive. The handrail must move at exactly the same speed as the steps, or passengers lose their balance. This synchronization is achieved through a secondary drive chain connected to the main drive system. The handrail itself is a reinforced rubber belt with a fabric or steel core, designed to grip the drive wheels without slipping. Tensioning devices maintain constant pressure on the belt, compensating for stretching that occurs naturally over time. Despite their similar appearance, there is no such thing as a universal escalator. Each installation is custom designed for its specific location. Indoor escalators used in shopping malls have enclosed mechanics and climate-controlled environments. Outdoor escalators used in transit stations require weatherproofing, drainage systems, and corrosion-resistant materials. Heavy-duty escalators in airports and subway systems are built with reinforced components to handle extreme passenger volumes, sometimes moving over 10,000 people per hour. Modern escalators are highly engineered and expensive installations. Costs vary significantly based on height, width, and environmental requirements. A standard indoor escalator for a 2-story building typically ranges from $100,000 to $250,000. High-capacity transit escalators with advanced safety features and weatherproofing can cost $500,000 to over $1 million per unit. Installation, structural reinforcement, and integration with building systems add substantial additional expense. A modern escalator is more than just a moving staircase. It represents a balance between mechanical precision, structural strength, and passenger safety. A good escalator moves people efficiently for decades, operates silently under heavy loads, and stops safely the instant something goes wrong. And if you'd like to learn how other types of mechanical systems work, let us know in the comments.